This is second module of chapter 8. In this module, a new kind of numerical method called predictor corrector method is used to solve first order ordinary differential equation. In this method, there are two types of formulae. The first one is called the predictor formula, and this formula determines the approximate value or predicted value of y, and this value is used in corrector formula to modify or update the value of y obtained in predicted formula. So, combining these two formulae, we get a method, and this method is called predictor corrector method. The trivial predictor corrector method is Euler's modified method or modified Euler's method. Now, we consider two predictor corrector formula. One is called the Adams-Basforth-Moulton method and other is called Milne-Simpson predictor corrector formula in this module. First, we define single step and multi-step methods. A method is called single step if only one value of the dependent variable, say yi, is required to compute the next value, that is yi plus 1. The Taylor series method, Picard method, Euler's method, Runge-Kutta method are the example of single step methods. On the other hand, a method is called multi-step if it needs more than one values of the dependent variable to compute the next value of the dependent variable. For example, in k-step method, the values of yi minus 1, yi minus 2, yi minus k minus 1 and yi are required to compute the value of yi plus 1. Now, we consider predictor corrector method. This method has two formulae. The first formula determines the values of y, approximate value or the predicted value of y, and it is known as the predictor formula. And the second formula, known as corrector formula, improves the value of y obtained by predictor formula. So, these two formulas are used in predictor corrector method. The commonly used predictor corrector methods are Adams-Basforth-Moulton, Milne-Simpson and many others. In this module, we consider these two methods, these two predictor corrector method to solve first order ordinary differential equation. Now, first we describe Adams-Basforth-Moulton method. The problem is dy dx equal to f of xy with the initial condition x equal to x0 and y equal to y0. It is a 4-step method, or it is called the 4-step predictor corrector method. That means, to find the solution of this method, we have to find the values of y1, y2, y3 before going to find the value of y4. That means, to compute the value of yi plus 1, 4 values yi minus 3, yi minus 2, yi minus 1 and yi are required. These values are called the starting values. To find these values, that means to find the starting values, generally any single step method such as Euler's method, Runge-Kutta method or any other method, say Taylor series method, Picard's method are used. So, using any starting method, that means single step method, we determine the 4 values yi to yi minus 3 to calculate the value of yi plus 1. Now, we integrate the given differential equation between xi and xi plus 1 and obtain the following equation: yi plus 1 equal to yi plus integration xi to xi plus 1 f of xy dx. Note that the second term cannot be determined because the function f of xy is given, but y is an unknown quantity. So, integration is not possible. To integrate the second term, the function f of xy is replaced by an interpolating polynomial. So, the function f of xy is approximated by Newton's backward interpolation formula, that is by the following expression: f equal to fi plus b into nabla fi, nabla is the backward difference operator, plus v square plus v by 2 into second difference nabla 2 fi plus v cube plus 3v square plus 2v whole divided by 6 into third backward difference of fi, where v equal to x minus xi by h and fi equal to f at xi comma yi. Therefore, yi plus 1 equal to yi plus h into integration 0 to 1, and the entire value within the square bracket is replaced by f of xy into dv. Note that dx equal to h into dv, and the lower limit xi is converted to 0 and the upper limit is converted to 1. Now we integrate this expression with respect to v and obtain this expression yi plus h into fi plus half h into nabla fi plus 5 by 12 h into nabla 2 fi plus 3 by 8 nabla 3 fi. After replacing the values of nabla fi, nabla 2 fi and nabla 3 fi, we get the expression given in equation 3. This formula is known as Adams-Basforth predictor formula, and it is denoted by, that means the value of yi plus 1 is denoted by yi plus 1 p. P indicates the predicted value. That means equation 3 gives the predicted or first approximate value of yi plus 1. Thus, the predicted value yi plus 1 p equal to yi plus h by 24 into this expression, that means equation 4 gives the predicted value. Now, to get the corrector formula, that means another formula, the same technique is used, but the function f of xy is approximated by the same formula, that means Newton backward interpolation polynomial. But the formula is this one, f of xy equal to fi plus 1 plus v into nabla fi plus 1 and so on, where v is equal to x minus xi plus 1 by h. So, using this expression, the given differential equation becomes this one, yi plus 1 equal to yi plus h into integration minus 1 to 0, and the terms within square bracket is obtained by Newton's backward interpolation polynomial into dv. After integration, the expression becomes yi plus h into fi plus 1 minus half of nabla fi plus 1 minus 1 by 12 nabla 2 fi plus 1 minus 1 by 24 nabla 3 fi plus 1. So, after using the values of first, second and third order backward differences, we obtain equation 5, and this is equal to yi plus h by 24 fi minus 2 minus 5 fi minus 1 plus 19 fi plus 9 fi plus 1, and this formula is called Adams-Moulton corrector formula, and it is denoted by yi plus 1 c. C for correction or corrector. Thus, the corrector formula is given by equation 6. Note that the last term is 9 into f of xi plus 1 comma yi plus 1 p. Since yi plus 1 is present in the right hand side of the equation 6 to calculate the value of yi plus 1, so for this reason this formula is called implicit formula. So, note that the predictor formula, that means the formula for yi plus 1 p is the predictor formula and it is explicit formula, but the corrector formula, that means formula 6 is the is an implicit formula. The value of yi plus p is computed from equation 4, and equation 6 can be used repeatedly to get the value of yi plus 1 to get the desired accuracy. Note that the predictor formula is an explicit formula, whereas the corrector formula is an implicit formula. This is very important issues of predictor corrector formula. Now, let us consider one example to illustrate the Adams-Basforth-Moulton predictor corrector method. In this formula or in this problem, the differential equation is dy dx equal to xy plus 1 y into sin x minus 1. The initial condition is x equal to 0 and y equal to 1. We have to calculate the value of y at x equal to 0.20 and y equal to 0.25. So, we have to calculate two values of y using Adams-Basforth-Moulton predictor corrector method. To calculate the starting values, that means the value of y at x equal to 0.05, 0.10 and 0.15, we use Runge-Kutta method. Here the function f of xy is equal to 2y minus y square and h equal to 0.05. So for these values, we applied fourth order Runge-Kutta method to find the value of y1. So first row of this table represents the values of xi, yi, k1, k2, k3, k4, and using this value we calculate the value of y1 and it is equal to 0.952419. So this is the first starting value. Similarly, we use the same formula, fourth order Runge-Kutta method, to find the second starting value y2, which is equal to 0.909377, and this is the third predicted value, third starting value, that means value of y3, which is equal to 0.870466, and y0 is given, that one is 0, y0 is given and that one is 1. Thus y0 equal to 1, y1 equal to 0.952419, y2 equal to 0.909377 and y3 equal to 0.870466. So these are the four starting values of the predictor formula. Now as per formula of Adams-Westport-Moulton predictor formula, the yp at 0.20 is given by this formula, which is equal to y4p, because y0 to y3 is given. So the predicted value is calculated at x equal to x4, that means yp at 0.20 is nothing but y4p, and the formula is this one. This is the values of f at x0 y0, f at x1 y1 and so on. After simplification, the value of yp at 0.20 is 0.83533. So this is the predicted value of y when x equal to 0.20. Now we use the corrector formula, this is the corrector formula, to update the value of y at x equal to 0.20. So in this formula we have substituted the values of y3, f of x1 y1, f of x2 y2, f of x3 y3 and f of x4 y4p. y4p is determined in previous formula, the value is 0.83533. So using this value we obtain this expression, and after simplification, value of y at 0.20 is equal to 0.83533. So this is the corrector value or corrected value, and previous one is the predicted value. Note that these two values are exactly same. So no further iteration is required to modify the predicted value or this new corrected value. Hence the finally y4 equal to 0.83533. So this is the value of y at x equal to 0.20, correct up to 5 decimal places. Now to calculate the value of y at x equal to 0.25, we use the predictor formula, this one. Note that in this formula the subscript of x, y are increased by 1 compared to the previous formula, and using the same values, that means the values of f at x1 y1, x2 y2, x3 y3 and x4 y4, we obtain this expression. After simplification it becomes 0.805461. Now we correct this value using the corrector formula, that means yc at 0.25 equal to y5c equal to this formula. Substituting the values of functional values at different points, we get this expression, and after simplification it becomes 0.80369. Note that there is some differences in predictor and corrector formula. So we have to repeat the predictor formula to modify or update this value. Now we use the same formula, the predictor formula, but the last term, that means y5p is replaced by y5c. y5c is the corrected value obtained in the previous slide, and using the modified values we get the value of or updated value of y at 0.25, which is equal to 0.80367. Hence, the value of y at x equal to 0.25 equal to 0.8037, and this value is correct up to 4 decimal places. So, we have determined the value of y at x equal to 0.20 and x equal to 0.25 using Adams-Basford-Moulton predictor corrector formula. The local truncation error for predictor formula, that means the Adams-Basford-Moulton methods, is this one. The integration h into integration 0 to 1 v into v plus 1 into v plus 2 into v plus 3 by factorial 4 into fourth difference, backward difference at xi yi, and after integration and replacing the four differences, we get the value of this expression, and it is approximately equal to 251 by 720 into fifth derivative of y at xi 1 into h to the power 5. And error for the corrector formula is h into integration minus 1 to 0 v into v plus 1 into v plus 2 into v plus 3 by factorial 4 into nabla 4 f I plus 1 dv. After integration and replacing the value of fourth difference, we get minus 19 by 720 fifth derivative of y at xi 2 h to the power 5. When h is small, then the local truncation error for Adams-Basford-Moulton method is minus 19 by 270 into y I plus 1 c minus y I plus 1 p. That means the difference between predictor and corrector formula into this factor. The Adams-Basford-Moulton predictor corrector formula is described. In this formula, the function f of xy is replaced by the Newton backward interpolating polynomial, and the polynomial is integrating between xi and xi plus 1, and after integration we obtain the predictor corrector formula. Now we consider another predictor corrector formula known as Milne's-Simpson predictor corrector formula, or shortly this method is known as Milne's method. In Milne's method, the function f of xy is replaced by Newton forward interpolating polynomial, and the polynomial is integrating between xi minus 3 to xi plus 1, and after integration we obtain two formula, one is predictor formula and other is corrector formula. The Milne's or Milne-Simpson method is used to solve the following initial value problem. The differential equation is dy dx equal to f of xy, and the initial condition is y at x0 equal to y0. Now we integrate the above differential equation between xi minus 3 and xi plus 1, and after integration we get this expression yi plus 1 equal to yi minus 3 plus integration xi minus 3 to xi plus 1 f of xy dx. Here also observe that the function f of xy is not integrable because the variable y is unknown. The function is known quantity, given quantity, but y is unknown quantity, and this is a function of y. So to integrate this expression or integrate the second term, we replace the function f of xy by approximating this expression with the help of Newton forward interpolating polynomial. That means the function f of xy is approximated by Newton's forward difference interpolation polynomial as f of xy equal to f I minus 3 plus u into delta f I minus 3, where delta is the forward difference operator, plus u into u minus 1 by factorial 2 into delta 2 f I minus 3 plus u into uy minus 1 into uy minus 2 by factorial 3 into delta 3 f I minus 3, where u equal to x minus x I minus 3 by h. Using this approximation, the equation 9 reduces to this one, that means yi plus 1 equal to yi minus 3 plus h into integration 0 to 4, and the term within square bracket is replaced by Newton forward interpolating polynomial, and dx is replaced by h into du, and the limit of x are changed to 0 to 4. After integration, yi plus 1 becomes this expression. After substituting the values of delta f I minus 3, delta 2 f I minus 3 and delta 3 f I minus 3, and after simplification, the value of yi plus 1 is given by this expression. Thus, the predictor formula due to Milne is given by this expression, that means the equation number 11. The predictor formula is this one, yi plus 1 p equal to yi minus 3 plus 4h by 3 into 2 into f I minus 2 minus f I minus 1 plus 2 f I. Now, the corrector formula is also derived from the same way, that means by replacing the function fxy by Newton forward interpolating polynomial, but the integration is taken between xi minus 1 and xi plus 1. In predictor formula, the integration is taken between xi minus 3 and xi plus 1, but in corrector formula, the integration is determined between xi minus 1 and xi plus 1. And the function f of xy is approximated by Newton's forward interpolation polynomial, that is f of xy equal to f of I minus 1 plus u into del f I minus 1 plus u into u I minus 1 by 2 into delta 2 f I minus 1. After this approximation, the value of yi plus 1 is given by this equation, and after integration, this expression reduces to yi minus 1 plus h into 2 into f I minus 1 plus 2 delta f I minus 1 plus 1/3 delta 2 f I minus 1. Replacing the values of delta f I minus 1 and delta 2 f I minus 1, the formula is changed to this expression yi minus 1 plus h by 3 into f of xi minus 1 yi minus 1 plus 4 into f xi comma yi plus f at xi plus 1 comma yi plus 1. Note that the value of yi plus 1 depends on the value of yi plus 1. So, this formula is the explicit formula. Note that in this formula, the value of yi plus 1 depends on the value of yi plus 1. So, this formula is an implicit formula. This formula is known as corrector formula, and it is denoted by yi plus 1 c. Thus, yi plus 1 c equal to yi minus 1 plus h by 3 into f at xi minus 1 yi minus 1 plus 4 into f of xi comma yi plus f of xi plus 1 comma yi plus 1 p, where yi plus 1 p is the value obtained by predictor formula. The predicted value yi plus 1 p is computed from equation 11, and this value is corrected by the corrector formula 13. If the value of yi plus 1 p minus yi plus 1 c, the absolute value of this difference is not sufficiently small, then use the corrector formula again to update the value of yi plus 1 c. And in this case, the predicted value is replaced by yi plus 1 c in the corrector formula. Let us consider one example to illustrate the Milne-Simpson predictor corrector formula. So, in this problem, the differential equation is dy dx equal to xy plus 2y, that means f of xy equal to xy plus 2y, and the initial condition is x equal to 0, y equal to 1. Our problem is to find the value of y at 0.20. Here f of xy equal to xy plus 2y, x0 equal to 0, y0 equal to 1, this is the initial condition, and h is taken as 0.05. Now, the fourth order Runge-Kutta method is used to compute the starting values y1, y2 and y3. The first row determines the value of k1, k2, k3 and k4, which are the parameters of fourth order Runge-Kutta method, and the value of y1 is given by this expression. That means the value of y1 is equal to 1.106553. Similarly, the values of k1, k2, k3 and k4 are calculated for the next value, that means to find the value of y2, and using this case the value of y2 equal to 1.227525 and the value of y3 is obtained by the same formula and it is equal to 1.365130. So, these are the starting values for the Milne-Simpson predictor corrector formula. So, these are the values of y1, y2 and y3. Now, the predicted value at x equal to x4, that means y4p, which is equal to y0 plus 4h by 3 into 2 into f at x1 y1 minus f of x2 y2 plus 2 into f of x3 y3, and these are the values of the function f at different points. After simplification it is equal to 1.521942. So, this is the predicted value of y when x equal to 0.2. The corrected value is calculated from the corrector formula given by the following expression y4c, that means value of y at x equal to 0.20 and it is equal to y3 plus h by 3 into f of x2 y2 plus 4 into f of x3 y3 plus f of x4 comma y4p, and these are the values of y3 and the value of f at different points, and after simplification it is equal to 1.52196. So, this is the corrector value of y. Again the corrector value of y4c is calculated by using the following formula y4c equal to y3 plus h by 3 into f of x2 y2 plus 4 into f of x3 y3 plus f of x4 y4, and these are the values of the functions f at x2 y2, x3 y3, f4 y4. After simplification this is equal to 1.52196. Note that last two values are same, therefore we conclude that the value of y4, that means value of y at x equal to 0.20 equal to 1.52196, correct up to 5 decimal places. Now, the error term, that means the local truncation error for predictor corrector formula are 28 by 90, fifth derivative of y at ci plus 1 into h to the power 5, which is equal to order of h to the power 5. This is the error in predictor formula, and the error in corrector formula is minus 1 by 90, fifth derivative of y at di plus 1 into h to the power 5, which is equal to order of h to the power 5, where ci plus 1 and di plus 1 are the constant lies between the first value, that means x0 to x4. In this module, two predictor corrector formulae are described. In first predictor corrector formula, that means Adams-Basforth-Moulton method, the function f of xy is replaced by Newton backward interpolating polynomial, and in second formula, that means Milne's formula, the function f of xy is replaced by Newton forward interpolating polynomial and integrating the polynomial in two different intervals. So, we can conclude that if we replace the function f of xy by another interpolating polynomial, we can derive or we can obtain another type of predictor corrector formula. In next module, we consider another important or interesting method called finite difference method.